think about us. We are sitting in front of two microphones. There are electronic chips in these microphones that would not work if it weren't for quantum mechanics. There's still a debate about whether light is an electromagnetic field. People are uncomfortable saying light is also an electromagnetic wave. That photograph is so iconic. I think something like 17 or 19 of those people eventually won Nobels.
Yeah. No matter how smart you are, you just cannot explain it through classical intuition.
I felt very uncertain, and I think that's just the nature of the field. I always felt like I was at the edge of whatever I was trying to write in terms of my understanding of it. Whenever you would talk to physicists, some of them would just say, okay, it's all in the math. You really need to look at the math. Quantum mechanics says that everything can be described quantum mechanically. You and I should have wave functions.
I think Einstein famously asked, right, if I'm not looking at the moon, does it mean it's not there?
These computations are all happening in different universes. If many worlds is right, then this app is supposed to help you make a decision. The idea is when light hits some metal, it will eject electrons. It's those electrons that constitute electricity for us. This is the essential mystery.
Anil, welcome back to a second episode. It's great to talk to you about AI and machine learning and so on. I think we'll change gear today and talk about something very different, but who knows, maybe very deeply related at some level as well, which is quantum mechanics. I have done actually a few episodes around quantum mechanics on this podcast. And one of the things, I want to emphasize that, while we may think quantum mechanics something very esoteric and, this spooky science that, no relevance to everyday life, but I think I want our listeners to know that in some ways, pretty much everything, that's a lot of modern life very heavily depends on quantum mechanics, the behavior of transistors which power, pretty much all of the semiconductors and computing age, lasers, MRI machines and so on.
Everything.
Right, everything, right? So quantum mechanics is very much part of it, just that, it's so deeply enmeshed and so very few people, take care of things and we can enjoy the fruit of the outcome without having to worry about it. But I think you have a knack of, picking these topics and, really bringing out the stories behind some of these things. And, book this very interesting title as well, Through Two Doors at Once. Now, I think anyone who had any slightest, physics education will recall this double-slit experiment, and and I guess late high school or early college, we will think of this. This showed us something about quantum mechanics. But I think what you argue in this book is this is a really seminal experiment which brought to the fore of how strange things are when you look at things from quantum mechanics point of view. In fact, your book, you quote this thing from Feynman. Feynman, one of his lectures, he says, one experiment which has been designed to contain all of the mystery of quantum mechanics to put you up against the paradoxes and mysteries and peculiarities of nature. So maybe in your own words, why is this particular experiment so important, and what motivated you to write the whole book about this?
Well, first of all, thank you for having me on this episode. I love this subject as much as I love AI. I think quantum mechanics is amazing. So, as a journalist, when I would write stories about quantum mechanics, oftentimes what would happen is the scientists that I would be speaking to, when you're trying to ask them, I really don't understand this, can you explain it a little more? Either they would say, oh, it's in the math, you really need to look at the math because, if you look at the math, it'll make sense. Or they would take the double-slit experiment as an example. No matter what concept they were trying to explain to me for their research, they would use the double slit as a way of kind of explaining a particular concept in quantum mechanics. And it was after having written multiple such stories for magazines that I realized that, hang on, this experiment, they keep coming back to it. So there must be something seminal about it. And like you said, we have studied this. Anyone who's done, undergraduate physics would have encountered the double slit experiment, and I didn't realize how seminal it was. And I also didn't realize, because when we study about the double-slit experiment in physics, we learn about Young's double-slit experiment, right? I mean, this goes back to 1800s when people were, debating about the nature of light. You had Newton, I forget, 1600s. He thought that light came in particles, like the corpuscular theory of light. But even during Newton's time, his compatriots like Huygens and others had suggested that no, hang on, there are certain things that light does, like refraction. When you go from air into glass and then back into air again, the fact that it changes direction, you cannot explain that if it is corpuscular, and you need a wave theory of light. So there was this competing idea that light is actually made of waves. And then Thomas Young comes along in the 1800s and very clearly does an experiment that shows light has, wave-like properties, right? And maybe we can talk a little bit about what the double-slit experiment is, just to set up So double-slit experiment is fundamentally extremely simple, right? You have a screen, just like imagine a white cardboard in which you cut two slits, very finely cut two slits.
So you basically take, let's say, a razor or something and just slice it through.
It has to be machined really well so that the edges are clean, etc. But let's imagine very finely, nicely cut slits. On this side of the screen, you have a source of light of one frequency, let's say red laser light. On the other side is another white screen, and you shine the light from this side. And the question you have to ask yourself is, what do I expect to see on the other side? And your intuition tells you that light is going to go through one slit or the other slit. So on the other side, on the white sheet of paper or white sheet of cardboard, white piece of cardboard, you should see two strips of red light, right? That's not what you see. So this is what I'm talking now is the classical Thomas Young experiment modified. What we see is that on the other side we see an interference pattern, which is basically strips of bright and dark lights. And in order to explain that, the only way you can explain that is to think of light as a wave. So the wave starts spreading from your source. Let's say you have a laser pointer. So the light is coming out as a wave, just like water wave is coming out. And then it hits the two slits. And then from the two slits on the other side, you have two sets of waves that start coming out. And this is, again, you can think of if you've been to a beach where there's a break wall that has two openings, and you have a huge ocean wave coming in. It hits the break wall, but then from the two openings, you have two sets of waves that start coming out. And then you will start seeing that they're interfering with each other. Somewhere the water is high, somewhere it's low, etc. Exactly the same thing is happening with light here. So by the time it gets to that white cardboard that you have on the other side, these two sets of waves interfere. And where the crest of one wave meets the crest of another, you get what's called constructive interference. There's more light there. Where the crest of one wave meets the trough of the other, you have a cancellation and you see no light there. So you get these dark and light regions. This is what Thomas Young did.
And from what I understand, so there are, from Newton onwards, people had this debate about whether light is made of particles or waves. In some way, Young's experiment conclusively proved that lights are basically waves, at least till that time, until Einstein, came along and he had this whole, explained again photoelectric effect.
Yes.
This whole, possibly, this particle nature of light as well. We'll come to that. But so far so Young's experiment, we are good with, light. Okay, light is wave. There's interference pattern. All is good. And then eventually, I think with electrons, I don't know who did the experiment, but someone's figured out that we can reproduce interference patterns with electrons. Now, electrons are supposed to be particles, obviously, and that just creates this whole mess of, around quantum mechanics.
Yes. But the studies with electrons actually are towards the mid 1900s. Even before that, people were beginning to. So if you look at the sort of the historical narrative, you have Young's experiment showing that light acts like waves. And then somewhere in the 1860s, you have Maxwell, who comes up with these laws of electromagnetism. And he combines electricity and magnetism to come up with a theory of electromagnetic fields, and shows that, a lot of nature is basically electromagnetic fields. There's still a debate about whether light is an electromagnetic field. And that's when, there's a lot of ferment around at that time, late 1800s. And we know that, electricity and magnetism can be combined, but light is still kind of standing a little bit apart. People are uncomfortable saying light is also an electromagnetic wave. But eventually, that also becomes very clear that light is also an electromagnetic wave. But one of the key things that happens in the early 1900s, well before the issue with electrons. In fact, I think in the early 1900s, we still haven't. I think electrons have probably been discovered. I forget the exact timeline here,
Yeah, Rutherford, I think.
yeah, J.J. Thomson, Rutherford, and others are figuring out that the constituents of matter are essentially, the nucleus and protons and electrons, etc. But those are all constituents of matter, right? And so on one hand you have matter, and then on the other hand you have electromagnetic waves. Then 1900, around that time, Max Planck is trying to explain this problem with black body radiation. It was a big outstanding problem in physics at the time, where you have a black body is something that is in thermal equilibrium, where you have incoming energy and then it is radiating energy and it's in thermal equilibrium. And if you think of energy as something that is infinitely divisible, like you can keep making smaller and smaller chunks of it, right? We tend to think of like this table, for instance. We can start chopping it into half, into fourths, and intuition tells us that we can keep chopping it indefinitely, which is not true. And eventually, you will hit atoms, and and that's the end of and then you get into electrons and protons. But at that time, people thought energy was infinitely divisible. And if you considered energy as infinitely divisible, then the calculations that you would do for the black body radiations were just haywire. It was not predictive of what was happening. And Planck was the first to suggest that no, energy has to be quantized, that it has to come in quanta, and that for a given frequency of whatever electromagnetic radiation, there has to be a smallest quanta of that energy, right? And that was one piece of work that happened, which set the stage for quantum mechanics. There was already a weird idea that something can't be divided any further. And then Einstein comes along in 1905 and explains the photoelectric effect. And the photoelectric effect, for those who don't know, is actually something that is very ubiquitous now, right? All our solar panels on our roof terraces are working off of that principle. The idea is when light hits some metal, it will eject electrons. And it's those electrons that constitute electricity for us. But what Einstein wrote and theorized about was this idea that when light hits a metal, the light has to be above a certain threshold frequency. For any given metal, there's a threshold frequency. If light is below that frequency, no electrons will come out, no matter how much light you shine on it. The moment you hit that threshold frequency, then electrons start coming out. And then if you just increase the intensity of light, more electrons will come out. But the energy of the electrons and the frequency of light are related, right? And he explained basically that he essentially said that you can only explain this if you take light to be quantized, right? And this was still not... even though on one hand Planck had said that energy should be quantized, the idea that light should also be quantized was not well accepted. There's a story about how when Einstein was being recommended to, I think, the Prussian Academy of Sciences, Max Planck was recommending him as somebody who should be admitted. And he basically said, everything he's done is amazing, and you should not hold against him the fact that he suggested that light should be quantized, right? Yeah. Because Planck at that point thought that was not right.
But eventually Einstein got the Nobel Prize for the photoelectric work.
In fact, the weird thing is, despite his work on special relativity and general relativity, the only Nobel he gets is for the photoelectric effect. Yeah, exactly. So, but this was the beginning, right? And then Niels Bohr. So one of the things that happens with these ideas that are happening with Maxwell's equations and the quantization of energy, etc., is people realize that if you take the standard model we had of the atom at that point, right? So J.J. Thomson and Rutherford had together all figured out the structure of the atom, which was essentially a nucleus with protons and neutrons and electrons that are orbiting. And Maxwell's equations were telling you that if the electron is orbiting around the nucleus, then it should be radiating energy, radiating light, and it would eventually spiral in, and the entire system was unstable.
Yeah.
Right. And so if you just held on to classical notions of what the atom was, it wasn't possible theoretically to exist. It couldn't exist. So Niels Bohr comes along and says that, hang on, maybe the electrons' orbits are themselves quantized in the sense that each orbit has some energy, and the electrons can only occupy particular energy states. And then when it comes to the lowest energy state, then it can't fall any further. So he kind of ad hoc made this it was a proclamation almost, saying that, as long as you can have this structure for the atom, it's stable. So all of the energy states are stable. And then the lowest one, the electron can't go any further down into the nucleus. So it was obviously not satisfactory, but it was the beginning, right? And these kinds of developments finally led people to this idea that light is an electromagnetic is electromagnetic energy, and that it can be quantized, and that not just light, not just energy can be quantized, but everything, electric fields and magnet, everything, any field can be quantized, and that there's a minimum quanta of that energy.
Yeah, and some of these, findings, as you said, the Max Planck's works and Einstein's work, and people finding, I think, initially electrons, and then figuring out nucleus is extremely tiny and actually dense, and that was Rutherford's work, I think. And that's led to this 20-25 years of, intense fervor and this whole, like totally new concept developments which culminating into quantum mechanics. And the reason I mentioned that is, instead, it is a great time to have this conversation. I think, this year around the world, people are starting to celebrate this 100-year centenary of quantum mechanics, which is quite amazing, I think, because around 25, 26 is when both Heisenberg and Schrödinger came with their own respective formulations, which, eventually turned out to be pretty much equivalent.
Right.
So, in fact, one of the very first global event around quantum mechanics is in Bangalore next week. If you're able to find time, and you should definitely join. But it's great. And, what's fascinating to me about this is, 100 years is also not that long of a time. It's just 1 century. And some of the most profound understanding that we have, and a lot of those relevant stories and science you cover in this book, is just basically 100-year-old. It's quite amazing.
Yeah, and maybe I should mention something that ties back to our previous conversation about AI, is that, there is a similar feeling when you attend conferences on large language models today. In fact, I've had this exact conversation with a researcher who said, this must be how it must have felt in the 1920s for physicists when they were sitting in conferences, classical physicists suddenly confronted with this weird thing. And people now are saying, okay, this is what it must have felt like when you're confronted by something you can't fully explain.
Yeah.
And 1924 was when Heisenberg came up with matrix mechanics, and then 25 was when Schrödinger did his wave mechanics, and then all of that came together in Max Born's stuff in 26. Bond was, I think, 26. Bond rule was 26, right?
And then Solvay conference is when they all kind of bore 27, right?
Yeah.
This is how it's going to be.
Yeah, and that photograph is so iconic. I think something like 17 or 19 of those people eventually won Nobels.
But it's, I think people are going to hear a lot about, I think, quantum mechanics, definitely in headlines, because I think the world is going to celebrate, rightly so. I think a lot of us probably don't realize how much quantum mechanics has changed our life and made it better and it is a weird science, the classical intuition. All of us still have very classical intuition, and therefore it becomes slightly inaccessible subject, and which leads to all these spooky things and paradoxes and so on. And therefore it's also very fascinating. I think writers especially have a field day with it.
Yes.
You are next time in some ways where you actually try to explain, where does all this mystery come from? And this, as you were saying earlier, this double-slit experience, ends up being at the heart of a lot of where these mysteries originate from.
Absolutely. I think, I think this is a good segue to talk about what is it about quantum mechanics that's so mysterious. And if you now think back to what we were talking about, the double slit, where you have a red laser light, you're shining it on the 2 slits, and on the other side, instead of seeing 2 bars of light, you see an interference pattern, which is easily explained if you think of light as a wave, right? That's not a problem.
Yeah.
Now, this was done at a time when we thought light was a wave, right? Of course, they didn't have laser lights at that time, but we are doing a modern version of the experiment with laser light. Now, imagine if you had the ability to turn down the laser light so that eventually all you're doing is emitting one photon of red light. Now, what quantum mechanics is saying that red light is of a single frequency, and there is a quantum of that energy. So, and that is a quantum of red light, which is one photon of red light, right? Now, your laser, your device is literally just emitting one photon at a time. Let's say one every second, right? On the other side is still the same apparatus. You got two slits, you got a screen on the other side, and you're asking the question, what do you expect to see? If you had some sort of pellet gun that was shooting grains of sand or whatever, right? You are very likely to just see two sort of strips on the other side where the sand is going to hit, right? And your intuition with this laser light, which is now just shooting one photon at a time, contrary to what we saw previously, which was an interference pattern, now your intuition says that, okay, now we know it's a single photon. Yeah. It has to go through this slit or that slit. If it goes through this slit, it's going to hit the screen right behind that slit. If it goes through the right slit, it's going to hit the screen behind the right slit. That's it. So you should now see them piling up behind. Let's say that's a photographic plate that is collecting photons over time. You should see two strips.
Yeah.
And the amazing part, and this is the weird thing about quantum mechanics, is that even if you just do a single photon at a time, over time on the photographic plate, what emerges are strips of dark and light and dark and light. So every single photon that you send will go to some regions only, which are regions of constructive interference, and will avoid those regions which are regions of destructive interference. So over time, when the photographic plate is developed, let's say you collect 100,000 photons over an hour or so, you will see the interference pattern. Now, you have created a single photon, you have detected a single photon, which is on both ends of the experiment, they are being treated as particles. But the interference pattern can only be explained if something goes through both slits. What is going through both slits?
Yeah.
Right? And so your intuition is saying, no, hang on, it has to go through one or the other slit, right? So let's say you put a detector. You somehow try to cheat and say, I'm going to see which slit the photon is going through. The moment you put a detector, the interference pattern vanishes. If you put a detector to see which path the photon is taking, on the other side, you'll see two strips. You take out the detector, you collect no information about what path the photon is taking, you see interference pattern. This is the essential mystery.
And what you cover in the book, and I think we'll touch upon some of those later, is this experiment has been done now with utmost precision, many different permutation.
Yeah.
And this phenomena is absolutely rock solid.
Yes.
And I guess our best understanding is that's just how nature is. We don't have any deeper explanation for this beyond that.
Well, we have a very, very good mathematical explanation for it, right? And that is in essence why you talked earlier of how quantum mechanics pervades our life right now. Like, think about us. We are sitting in front of two microphones. There are electronic chips in these microphones that would not work if it weren't for quantum mechanics. This is being then transmitted. There are CCD cameras that are recording us. Those are quantum mechanical. Eventually, people are going to listen to this stuff on their laptops or their smartphones, which would not work without quantum mechanics.
Yeah.
It's quantum mechanics everywhere, right? So, I mean, it's basically almost unimaginable how pervasive this is. All of that wouldn't work if we did not have a strong mathematical understanding of how to describe what's happening, right? So the mathematical description, it starts with, let's say, if you have a single photon, which is a unit of energy. Normally, if I was doing something in the classical world, the world of everyday objects, like if I had a baseball or a cricket ball and I was throwing it, right? You would have some knowledge about the initial conditions of your cricket ball, and that would represent the state of the cricket ball. And then you would throw it, and you would use Newton's classical mechanics to completely chart the trajectory of the cricket ball in a very predictive manner. As long as you know the initial conditions completely, which is the state of the ball, and the forces that are acting on it at the moment you release it, your entire trajectory is determined, right? You know exactly where it's going to go. In quantum mechanics, however, when you start with the photon, the initial condition is described by something called a wave function. The wave function is not a description of exactly where the photon is. It's a description of the possibility of finding the photon in various places, right? So if you were to look for the photon here, the wave function gives you a certain probability. If you were to look for it here, it tells you that, oh, the probability of finding it is here. But when you're dealing with a point-like particle, at the point of creation, the wave function is very sharp, which means that it's very likely to be found in one place and nowhere else, right? So that's the beginning. And then, unlike in classical mechanics where you can tell the position and momentum of the particle as it's traveling through space, in this case, all you can talk about is how the wave function is evolving over time, which is what Schrödinger figured out. He said, Schrödinger's equation essentially tells you how the wave function deterministically evolves over time. So that's all you can tell. So if it's just a wave, it was a sharply peaked wave here, and you release the photon, the wave function starts spreading. So by the time it comes to the double slit, before it even hits the double slit, the wave function is spread out. It's a wave. Yeah. But it's a wave of what? It's a wave of probabilities. Right? It's not telling you that the photon is a wave. It's just telling you that the probability of finding the photon here has changed relative to what the state was before. So all you're doing is evolving the quantum state of the particle using Schrödinger's equation. And it's that wave that hits, mathematically speaking, it's that wave function that hits the two slits. And then on the other side, it's the wave function that is propagating. But it's very unclear what that is. Mathematically, you can show exactly what's happening. So by the time you reach the screen at the other side, you have two wave functions that have interfered. So now you have different probabilities of where the photon will be. And when you detect it using your photographic plate, the probabilities bear out in the sense that if you send 100,000 identically prepared photons from one side, over time, you'll see that the probabilities are exactly what the math says it should be. Right. But you can never tell where a single photon is going to go.
Yeah. And I think the central importance of this experiment comes from the fact that there's, no matter how smart you are, you just cannot explain it through classical intuition, that logically how, using baseball analogy, or I guess in Feynman lectures, Feynman talk about, shooting bullets.
Yes.
They will just cluster around, whichever state they happen to go through. Yeah. Versus the photons and other particles behave as if they are in some ways going through both slits simultaneously and interfering with each other constructively or destructively. And this is just, in your face, it's right there. You can see it, any of us can see the tons of pictures and videos on the internet. People can go Google and see all this interference pattern, including, experiment with one photon at a time, one electron at a time. Yeah. And that is just, it's a smoking gun of quantum mechanics. They just cannot, you cannot ignore it.
Yeah, no, I completely agree. I think just about anyone you talk to in the field will tell you that this experiment really, as Feynman said, it embodies the central mystery. And, one of the key, there are many, many key ideas that underlie quantum mechanics. And one is the idea of superposition, right? The idea that a quantum system can be in multiple states at the same time, right? So in this case, in the double slit case, it's in a superposition of having gone through the left slit and having gone through the right slit. Superposition does not mean that it has gone through both slits or it has gone through one slit or the other. It's just a mathematical description saying that there were two states, possible states, and there's a mathematical way of saying that those two states coexist until you make a measurement.
Yeah. Now, going back to your process of writing this book, so now you zeroed on this particular experiment, and you kind of traced nearly 100-year history until some experiment all the way to recent times, and perhaps some in the near future as well. What was your just big learning through this whole process about how did your understanding about the field evolve as you went through this 100 history and our kind of wrestling with this particular experiment with ever more refined versions of this?
I remember this book as being very hard conceptually. I felt very uncertain, and I think that's just the nature of the field. I always felt like I was at the edge of whatever I was trying to write in terms of my understanding of it. And fortunately, it worked out. But it was a challenge. I back in college, I have done a course in quantum mechanics, but at that time, I don't think I paid attention. Just got through it somehow. So for this book, I had to relearn some of the math because, again, like I said, whenever you would talk to physicists, some of them would just say, okay, it's all in the math. You really need to look at the math. So I tried to understand the math up to a point. And there came a point where I said, okay, now I get it. Like I get what they mean when they say it's in the math. Like what does superposition mean mathematically, etc. Or what does entanglement mean mathematically? So once conceptually I got it, I felt like, okay, I don't need to figure out how to solve the Schrodinger equation. That's not the purpose of this. I need to understand what the Schrodinger equation does conceptually and what does a quantum state mean and what does it mean to evolve. So those kinds of things, it took a while. But then each of these experiments, like you said, it's a 100-year history, right? And the experiments kind of start in the early 1900s and then they keep going all the way until even as recently as 2015, there are things that people are doing that continue to probe this mystery. It's almost like I felt like these experiments themselves were like a crime thriller. You're trying to kind of fool the photon or fool nature to somehow say, I'm going to do a more sophisticated experiment to somehow get underneath your mystery. And nothing so far. Right? We're still.
Let's talk about the mystery in some more detail, right? And so look, so you mentioned that initial this one photon at a time experiment, which I'm assuming maybe I think the technology probably took some time to catch up to that point where we can actually do experiment one photons. But people are also quite surprised when they were able to see these interference patterns with electrons.
Yes.
Because light, okay, maybe wave, maybe particle, maybe I can have this, interference and so on. But electron is absolutely unexpected. You would not expect electrons, which is a particle, pretty much like miniaturized bullet or sand grain to interfere with. So that was a pretty big.
Yeah, and so that and again, hints to wave particle duality were all not even hints. Actual theories were already there, right? De Broglie had already come up with the wave particle duality as a central idea that everything can be described either as a wave or as a particle. But when they actually did the experiment with electrons, it was nonetheless still a surprise, right? The idea that again, conceptually, it's a double slit. You basically have a very, very thin charged wire, something like 3 microns thick. And I think relative to that, human hair is 100 microns or something like that. So this is a very thin charged wire. And you're firing a stream of electrons. And when the electrons see the charged wire, they either take this path or this path. They kind of bend around, just like water would bend around an obstruction. And then on the other side is a detector that is detecting the electrons. And logic tells you that you should just see them kind of hitting one side or the other. And it turns out, no, they, essentially, any time you have a particle or a quantum system that can have multiple states, in this case, going through the right of the charged wire or through the left of the charged wire. And if you don't know, once you detect the electron on the other side, if you don't know which path it took, then it will act like a wave and interfere. And you will see the interference pattern. So, but the moment you try to see it, and that's the key, right? The interference pattern disappears when you try to detect what path the electron is taking. And that's also a very crucial mystery because that embodies another very important aspect of quantum mechanics, which is that what's happening when you try to detect what path the particle is taking, whether it's a photon or electron, is that the photon gets entangled with the environment, which in this case is your detector. And the entanglement causes the interference pattern to disappear, right? So in a sense, the double-slit experiment has, questions you can ask about what is the nature of the wave function. Is it real or is it just mathematical, right? You can ask questions about what does superposition mean? What does it mean to exist in multiple states at once? What does entanglement mean? All of these things are kind of baked into the experiment, and it is such a simple experiment conceptually.
And you trace the history of people have been trying to do this experiment with bigger and bigger molecules and so on. And in at least one of the attempts of trying to fool it, you maybe expect some level will stop. But so far, the like people who've gone up to, I think you describe in the book, something like 10,000 times bigger than a mass of a proton.
Yeah.
And yet the interference pattern just keeps showing up.
Yes, and this has something to do with some of the interpretations of quantum mechanics, right? The reason why some people think that at some point when you start sending bigger and bigger things through the double slit, the interference pattern should go away, is because they think that there is a quantum classical divide, that there are things below a certain mass scale will remain quantum, which means that they can exist in a superposition of states. But the moment you go beyond that mass scale, the superposition should collapse, and it should collapse into one of those states. And then it becomes a classical object that you can have a definite location, a definite momentum, all those things. And again, these are just theories. People have interpretations of the math and ideas about what should be happening. And so they're testing it. They're testing by sending bigger and bigger, things through the double slit. I think they've even tried to send a virus particles through, but the virus keeps breaking up, so it doesn't work. Right now, I think, at least when I wrote the book, the record was something like 10,000 atomic, 10,000 protons or something like that, 800 atoms or some number like that. Very large atoms.
Yeah.
I'm sure the number has increased by now.
But when you looked at these experiments, talk to these, what is their motivation? Like, these scientists, what are they trying to do? Because now we have such solid history of this particular experiment. Where do they want to get to?
To understand the nature of reality, right? So the mathematics is telling you something. The mathematics is telling you that even a large molecule, if you are treating it as a quantum mechanical object, and quantum mechanics says that everything can be described quantum mechanically. You and I should have wave functions, right? So in quantum mechanics, there is no indication of whether it should apply to things of this size and not this size.
Yes.
As far as the theory is concerned, it's universal. So it should apply to everything. And so the math is telling you that this is how it works, but the math doesn't really tell you what is the underlying nature of reality, right? What is the wave function? If the wave function is real, then it makes sense that something should go through both slits. Something real will go through both slits and interfere, and you will see. But the moment you assume that the wave function is real, then you land up in a completely different soup of problems. And this is something that Einstein had pointed out, right? So for instance, take a single electron, let it start traveling. So quantum mechanically, its wave function is spreading, right? It's spreading, over a large area. So which basically means that the probability of finding the electron in various places is changing. And then at some distance, there's a detector that detects the electron. He pointed out that the fact that you can detect it in one place also tells you instantaneously that it's not in any other place, right? So there is an instantaneous collapse of this. If it is real, something has collapsed instantaneously across a wide region of space-time. And that completely contradicts the Einstein's own theories of relativity, which is basically saying that no influence can travel faster than the speed of light. In this case, something that happened here had an immediate effect on something very, very far away, because something very, very far away instantly knew that the electron is there or wherever. It's not there, right? So the moment you assume that the wave function is real, and if that is the nature of reality, then it creates a lot of other problems. If you assume it's not real, that it's just a mathematical abstraction, then you're left with the problem of trying to explain what went through both slits, right? Obviously, your photon is not going through both slits because quantum mechanics has very clearly shown that that's an indivisible unit of energy. You can't divide it any further. So it can't split and go through both slits. So there's this fundamental problem you're confronted with trying to explain what is the most basic way of thinking about nature. So for almost all these people who are doing these experiments, that is the curiosity. Like, what is it underneath all this?
And is that also sparking a kind of new wave of there are foundations of quantum mechanics, kind of revisiting? Because as I understand it, almost around, in late 20s, this last century, not this century, is... Bohr and these guys, they agreed on the so-called Copenhagen interpretation, and said that's the official dogma. We are not going to talk about this. Let's keep making math better and better, which they did to astounding ability, and also huge amount of technical progress to be able to do all kind of things with it. But this whole, what does it all mean in terms of nature of reality? And there have been a couple of interpretations in between the pilot wave theory and
many worlds,
interpretations, so on. But now popular media likes those stories. We have all these big science fiction movies also about parallel universe and whatnot, but not so much mainstream science until recently. But do you think there is a renewed interest in going back to this foundation?
Yes, there is very much a renewed interest in the last 2 decades or so, because I think now we have the kind of both experimental tools and sort of the mathematics to start asking more foundational questions. So the Copenhagen interpretation that you mentioned due to Niels Bohr and a group of people, including Heisenberg. So Schrödinger and Einstein were not part of that, right? They were against that. And because one of the fundamental thing that the Copenhagen interpretation does is it basically says that it's what's called an anti-realist theory, right? It's essentially saying that the photon has no existence until it's measured, right? So if you say it has an objective existence before your measurement, then you're confronted with the problem of trying to explain what it's doing as it's going through the slit. If you just completely ignore that, they basically say all that we are concerned about is the mathematics, which is telling you what the wave function is doing. The photon comes into existence only when you measure it at the detector. Right. So it denies objective reality before measurement. Right. And for Einstein, Einstein was a realist. He basically said, hang on, nature has to exist regardless of whether you and I measure it, right? The nature needs to have its own properties. It has to be doing its own thing. We just happen to measure it and see what it is. This idea that we actually bring reality into existence during measurement was just anathema to him. Right? So the Copenhagen interpretation didn't sit well with a lot of people for this reason. It is anti-realist and it kind of wishes away. I mean, it's not that they're wrong. It's just that there are other ways to think about what might be happening. And so you mentioned the pilot wave theory. So de Broglie had already done some of the work and dropped it in the 1920s because people, I forget who it was, maybe Pauli who went after him, and Pauli was a big name and somehow that theory fell apart. But then David Bohm independently discovered and did a much more rigorous mathematical analysis of what can be called the pilot wave theory. Now it's called de Broglie-Bohm theory, and that essentially says that the photon or any quantum particle is always a particle, but there is another wave, pilot wave, that is propagating, and which is the one that's going through both slits, and the particle is riding on these waves, and so its trajectory is not like a straight line that you would see if it was a straight particle. It's actually being buffeted by the underlying wave. So there is a reality that they are positing that exists underneath all this. Right, and then there were many worlds people who said, Everett, who was the proponent of that, he basically said, no, hang on, the simplest thing we can do is take the mathematics for what it is. Make no other, the most conservative approach you can have, saying that all we have is the mathematics. It's clean and beautiful and elegant, and we should not be making any more additions to this. Let's see what it says. And one of the outcomes of that way of thinking is saying that all possibilities exist in their own worlds. So if a photon went through the double slit and you detected it here versus here, then it's essentially saying that in one world or universe, however you want to think about this, it is actually here, but in another world it's also here. So every time there is a quantum fork in the road and the quantum system does two things, the universe splits and becomes two things. And you can imagine, and for those who are only looking at it mathematically, it seems, oh, this is great. It's but instantly you start having this unease about what do you mean? At every fork in the road, the universe is splitting into another. So you can see the obvious objections that come up.
Not by Hollywood, but yeah.
Not by Hollywood, yes. And then this continues, right? So now you're confronted with trying to deal with this essential mystery of what is the wave function? Is it real? or is it just epistemic? Is it just our understanding of, the nature through some mathematical abstraction, that there is nothing real there? And regardless of which one you take, you end up with problems. If you take an epistemic approach, you get into trouble in one way. If you take what's called an ontological approach, which is saying that the wave function is an essential part of the reality of the universe, that there is something actually there called the wave function, then you end up with other kinds of problems. And no interpretation or theory. So interpretation is just taking the standard quantum mechanics formulation and interpreting it in one way or the other. But there are other theories. So one of the problems with the Copenhagen interpretation has been this so-called measurement problem. Right? What Bohr said was that you will see either the wave nature of the photon or the particle nature of the photon depending on what you choose to measure. If you choose to measure its particle nature, you will see particle nature. If you choose to measure the wave nature, you will see the wave nature. And he put the onus on the measuring apparatus, but nowhere in the Copenhagen interpretation does it tell you what a measuring apparatus is. How big does that have to be, right? Yeah. It just basically says that there is this quantum system, and whatever is doing the measurement is a classical system. Yeah. It doesn't tell you anything about what the divide is. Where should something go from being quantum to being classical? The other thing it says, mathematically speaking, is that it says the moment you make a measurement, it causes a so-called collapse of the wave function. The wave function which was spread out, which meant that the photon could be in a superposition of many states, the moment you measure it, the wave function collapses so that it peaks at one point and the photon is there and it's nowhere else. Right? But that collapse is due to the act of measurement. And it puts the onus on the measuring device or the people making the measurement. And that also did not sit well with a lot of physicists, right? So they came up with theories that were trying to be so-called observer independent. They, Einstein would have been like that. To him, it would have been like the measurement just if indeed collapse is happening, then the measurement discovers the outcome of the collapse, doesn't cause the collapse. Right. So there are a whole bunch of theories that are like that.
I think Einstein famously asked, right, if I'm not looking at the moon, does it mean it's not there, right? So to just mock this whole idea of,
Yeah. I don't, did he say that?
I think so.
Okay, yeah. Yeah, I remember that quote. I forget where I had seen it. But yeah, no, exactly that, right? And John Bell had very caustically asked, like, so if the universe was one single wave function evolving, what was it waiting for to collapse? Like PhDs in physics before it collapsed, right? So,
yeah. And maybe let's talk about John Bell a little bit, because I think he also had a pretty seminal contribution, with this whole, so I think you alluded to this whole entanglement thing, and Einstein, came up with this whole EPR paper to try to, in some ways, postulate that there's something fundamentally wrong with quantum mechanics. If quantum mechanics will imply that there is act of measuring something here can instantly communicate something over there.
Yeah.
And John Bell, I think, rigorously, devised experimental approach to be able to measure that. And people have gone ahead and did those experiments. And now we know entanglement is real, and it, does not communicate information, but does lead to kind of simultaneous determination at it could be other end of the universe also. Yeah. And that's part of the reality that we live in.
Maybe we can just discuss briefly what the EPR paradox was that Einstein came up with, right? So, so the idea here would be that, let's say you start with a system that generates two photons that are that set off in opposite directions, right? And they are polarized. Yeah. And so when you are describing the polarization is just something like spin. Let's say if you measure the polarization of a photon in one direction, it can be either up or down. And because these started off from the same system, they are set to be entangled, in the sense that if this photon, if you measure it in the vertical direction and you find it to be up, then this one will be down. And if you measure this and find it to be down, then this one will be up. So they are said to be entangled. But here's the thing, right? You set your system off, the two photons are proceeding in opposite directions. If you were to just try and measure mathematically say what is the likelihood of finding this photon polarization in the up or down, it'll be 50%. So you cannot definitively say that photon A, which is going to the right, has a certain polarization. You can only say it has a 50% chance of being up or 50% chance of being down. Same thing for this one, right? You cannot definitively say what it is. Now, you make a measurement. The moment you make a measurement on photon A and find it to be up, then without even measuring that, you can definitively say that it will be down. Which is the amazing thing, right? The idea, until then, you can only make probabilistic statements about the two, but the moment you make a measurement on one, even if this thing is light years away, you know now that that thing has the opposite polarization. And that was Einstein's essential problem. He was saying that, well, that kind of means that something has happened where something that you did to photon A instantly affected photon B, which was way too far away for the influence to have traveled at that, So in his theories, the influence has to travel only at the speed of light, right? And so his contention was that if you're using quantum theory to explain this phenomenon, then quantum theory is incomplete. That there must be some underlying reality that captures the fact that photon's polarization was always down, and you couldn't explain it using quantum theory. You could only talk about it probabilistically, but actually it has that value, and you need to kind of supplement the theory to come up with a more fuller theory, which is what David Bohm did. So Bohmian mechanics is essentially what's called a hidden variable theory, that there are other variables that capture that information and make it a deterministic theory. So when John Bell came, he was enamored by Bohm's work, right? So he thought Bohm had done the impossible of, because the reason why he said it's done the impossible was in the 1930s, John von Neumann had kind of wrongly, it turns out, but at that time, very persuasively proved that you cannot have hidden variable theories. Right? It turned out to be the proof was wrong, but it was very influential when it came out, and people just thought that you will never have a hidden variable theory. And then Bohm comes and develops what hidden variable theory for quantum mechanics. So, and Bell looks at it and says, he's done the impossible. Basically, von Neumann had said it was impossible, and Bohm showed that, no, it's not impossible. At least you can have a theory. And like you were saying earlier, Bell he realizes that you can have a very formal mathematical framework to test these ideas, right? So if these particles are going in different directions, he figured out a way to show that if there is an underlying reality, then when you make a series of measurements on identically prepared particle, the correlations that you would see between a measurement you make here and a measurement you make here will be below a certain threshold if Einstein and hidden variable theories are right. But it will be above a certain threshold if quantum mechanics and this so-called non-locality is correct. And he ironically had designed it because he thought Einstein and Bell were right. But what happened was that as people started doing the experiments, it turned out that quantum mechanics was right. That at least, to be fair, this theory, Bell's tests don't rule out Bohm because they're not really testing David Bohm's idea of sort of hidden reality, but they are ruling out a particular kind of hidden variable theories that Einstein was in favor of, which are what are called local hidden variable theories, where you have hidden variables, but also no influence can travel faster than the speed of light. Bohm's theories are non-local. So if something happens here, it instantaneously influences everything everywhere in the universe. Completely non-local. And so those are not ruled out by Bell tests. But there's been a series of Bell tests since, 70s onwards. Every decade they've been doing more and more rigorous experiments, and so far quantum mechanics is right.
And all this may sound little complicated and so on, but anyone who's interested in understanding how does our world works, and these are the fundamental building blocks of how the world works, and this is the best possible both theoretical and experimental understanding. And especially for quantum mechanics, it just keeps passing every possible test that's thrown at it, and no workaround around the so-called mystery, which is how it's just nature seems to work. It's like it that way, and whatever we are able to do, we just keep confirming it ever more precision. That's just how things are. So it's again, maybe it's definitely strange. Often sounds complicated, but there is the genuine understanding of the world we live in, including what we are made of. It's this is how it works.
Yeah, no, and exactly, we are made of the same stuff as everything else, and if quantum mechanics is the correct theory of nature, and according to the theory, it should apply to matter at all scales, matter and energy at all scales. But our experience of the world is very clearly one of classical mechanics, right?
Yeah.
Things are not in two places at once. We are always in one place at once. So there is something that remains unexplained. So there are many mysteries. Like, is there a quantum classical divide?
Yeah.
Right? We don't know. Right? Quantum mechanics says that there is none, but things like the Copenhagen interpretations imply there is one. There are theories like what are called collapse theories that basically say that when the mass of the quantum system exceeds a certain threshold, its wave function stochastically collapses to one of the possible states, right? So those theories are also suggesting that there is a quantum classical divide. Roger Penrose has a collapse theory which basically says that the collapse happens because if you have two masses that are in superposition of being here and being here, we know from Einstein's theories of general relativity that mass will curve space-time.
Yeah.
Right. And Penrose points out that having multiple curvatures of space-time is unstable, and that as long as the mass is very small, it's okay. It will persist. That instability can persist for a while, so the mass can exist in superposition. But if it gets beyond a certain scale, then space-time configurations will collapse to one or the other. So that's also a collapse theory. But then there's many worlds, which basically saying there is no collapse. Every eventuality is manifest.
But many world is, I would say, probably out of fashion by now.
No. I mean, you will find very strict adherence to that. Yeah. No. It is still very much, including people like David Deutsch, really well-known physicist, Sean Carroll. There are multiple people, very well-regarded physicists who find that the most appealing explanation. There are even people who will, this probably, in my mind at least, I'm not a many worlds fan, but then I'm kind of agnostic because I don't have the mathematical capability to take a stance on it. This is just me being a storyteller. But there are ideas, like we are seeing the birth of quantum computing, right? And quantum computers are able to do what they do because superposition they take superposition for given.
Yeah.
They use the fact that a system can exist in a superposition of states that allows multiple computations to happen simultaneously before the collapse happens.
Yeah.
So the way people like David Deutsch have argued is these computations are all happening in different universes. So I don't know what to make of all this, but many verse has not gone away at all. So I would be hard-pressed at this point to point to any interpretation that is particularly favored.
Yeah.
The Copenhagen interpretation is still the most effective in terms of, in the sense that it simply says, shut up and calculate, right? Do your math, and that can help you do your experiments and build your systems, and it works. So that shut up and calculate phrase is very common. And a lot of people, there's enormous work that has happened in chemistry and
live in very woke world now. No one's going to shut up anymore.
Yeah, possibly. Yeah. But like you said, the interest in the foundations have come back in the last 2 decades because people are increasingly now coming up with a lot of theorems that are designing thought experiments. So they design a theorem. It's called a no-go theorem. It makes certain assumptions about the nature of reality. And then using that theorem, they will propose a thought experiment. And they will point out that if you do this thought experiment, you will end up in some sort of contradiction. And the only way to resolve the contradiction is to question one of your assumptions. And Now, it doesn't say which assumptions. You can, depending on which assumption you question, you are choosing one of the many interpretations. So, and they're all in the running. No, but none have been ruled out.
Got it. And I think with this renewed interest, hopefully maybe, who knows, whether we'll have a deeper explanation or not, but at least probably candid explanations may emerge. And I don't know if you have picked up anything, you feel.
So there is one very interesting development that is happening, which may or may not crack this case. But so when Einstein came up with his theories of relativity, one of the big things that happened was this idea of reference frames, right? We've all read about those sort of toy experiments in special relativity when, somebody is standing on a train and throwing a ball up and down, right? Or throwing a ball up and catching it. And for the person in the train, the ball is just going up and down. But if you're standing on the platform and watching the train go by and watching this person throwing the ball takes an arc, right? So those are measurements done from two different reference frames that are in relative motion. And depending on which reference frame you are in, you have a different perspective on what's happening. But they're equivalent. You can translate from one reference frame mathematically to another. The system is one physical system. Quantum mechanics, until very recently, has always taken as a fact that there is a universal reference frame, right? Like we talked about the EPR experiment where a photon is going this way and a photon is going this way. There is a measurement that is done on the right side, a measurement that's done on the left side. In quantum mechanics experiments, there's always these two people called Alice and Bob. So Alice is on one side and Bob is on one side. In quantum mechanics, Alice and Bob have always been in the same reference frame. Only now are people beginning to say, hang on, why are we making that assumption? Why are we making the assumption that they share the same reference frame, right? What if the reference frame Alice inhabits is different than the reference frame Bob inhabits? And because this is quantum mechanical, the reference frame themselves can be in a superposition of being here or whatever, right? So the early mathematics is suggesting that your choice of reference frames can suddenly dissolve certain paradoxes. So things are paradoxical because we've been assuming this universal reference frame. For instance, time. Time is relative in classical physics. In quantum mechanics, time has been this master clock that has been ticking away outside for all, right? And it's not specific to any reference frame. There's always one background clock which doesn't make sense. That on one hand, you have classical physics where time is integrated into your theories, and here you have a clock that's ticking away independent of. So maybe the mathematical formulations that are beginning to come that start dealing with quantum measurement systems as being located in reference frames and that everything is relative to the reference frame. It's early days, but the sense I get is there might be some resolution coming from there.
Got it. It's exciting. I think people are thinking about these things seriously and trying to formulate some rigorous explanation for what an alternate way to think about or understand some of these things. And again, these are not very esoteric philosophical concept because you earlier mentioned quantum computing, and earlier we did a whole episode also on quantum computing as well. They are very much here and starting to become fairly powerful. There's many hundreds of qubit systems, and the superposition is the critical ingredient of how these things work. So it's no longer a just vague hypothetical thing. Tomorrow we might be using these devices directly, indirectly, or the output of these devices, which again quantum mechanics at the heart of it. The more we understand, both as a layperson as well as hopefully the scientific community makes progress about what these things are.
It is amazing because finally it's really about understanding nature and our place in it, right? And it's and this is nature at its deepest level. For instance, if many worlds is right, then I remember when I had gone to meet Sean Carroll in Caltech, he took out an app which was called the Universe Splitter app, where you could use that app to send a command to experiment near Geneva. And in Geneva, what that experiment would do is it would shoot a single photon at a beam splitter. And the beam splitter is just a transparent piece of glass that sends the photon with 50% probability this way or 50% probability this way, right? That's all it does. And essentially, this thing is, if many worlds is right, then this app is supposed to help you make a decision. It's basically, you're conflicted about making this decision or that decision. So the app is basically saying, look, it doesn't matter. You make this decision in this world, and in the other world, you will make the other decisions. So why are you anxious? All that app will tell you is, at least in the world that you are interacting with right now, you can either do this or that. And just rest assured that the universe has been split, and in the other universe, you've taken the other decision.
If you remember the name of the app, you should mention, I think
it's called the Universe Splitter app.
Universe Splitter app. So there you go. I think for people who have persisted with this episode so long, this is your reward. You can go and split the universe, and that'll be your legacy.
Yes.
But this phenomenal, Anil, I think it's really amazing to see kind of work you do, and this putting so much effort to bring out this difficult concept in a way where it can be communicated to people who have interest in science, without really compromising on scientific rigor. I think you don't carried away with speculative thing and all the mumbo jumbo that a lot of people weave around these things. You're staying on the right side of fairly rigorous science, and yet trying very hard to bring out the stories alive and the implications. And I thoroughly enjoyed reading both of your book. Hopefully a lot more on the way along these lines. I think we live in a world which is immensely affected by science, and the more all of us understand in our own way, in some ways going to enrich our lives.
Well, thank you for saying that. And I also appreciate the fact that people like you are doing these podcasts where we talk at length about these subjects, because that's another big way in which we can reach out to the broader culture. Because I think, like you said, these are ideas that are impacting us all. And the more we get familiar with them, the better off all of us will be. So thank you very much.
Absolutely. Thank you.
At Sparks, we aim to bring to you stories of exponential impact. We share in-depth analysis of what goes behind success stories. If you find our conversations interesting, you can join us by subscribing to our YouTube channel. You can also listen to Sparks on Spotify, Apple Podcast, or any other audio platform of your choice. If you have any suggestions on who we should invite or what topics we need to cover, just let us know in the comments. We are always listening, looking for ways to improve, and keep getting better as we go along.